Hello, and welcome to lesson 16 of this Introduction to Probability of Wolfram U. The topic for this lesson is the uniform distribution. Let's begin. Do you remember lesson 5 where I covered different common assumptions? This lesson, we study the distribution of the most common assumption, that is, the assumption of uniformity. This assumption describes a continuous constant rate constrained by a minimum and a maximum. This distribution is considered a strict representation of continuous equiprobability, a concept studied at the very beginning of probability theory with Girolamo Cardano. The simplest distribution in the discrete case is the Bernoulli distribution, with only two probabilities that add up to 1. In the continuous context, the simplest distribution is a single probability with an infinity of values. In other words, a constant function. For a constant to have an integral of 1, you need a minimum value and a maximum value. So imagine a rectangle on a graph, from minimum to maximum, where the area needs to be 1. The length is naturally the maximum minus the minimum. So the height, or probability, must be 1 divided by the max minus the minimum. And indeed, that's the case, as you can see from the PDF. Simply taking the integral, you get the CDF, a function with a constant rate of increase. Note that the uniform distribution can be both univariate and multivariate. For example, you can plot the CDF of the bivariate uniform distribution with the minimums at 1 and the maximums at 3, which looks like this. If values have the same probability from min to max, then the average of min and max should be the average of all values, as it's symmetrical. And this is indeed the case, as you can see from the mean. The variance is a variation squared, so intuitively it should be proportional to the square of the difference between the min and the max, as a large difference would mean more dispersed values, and so variation. The most common assumption does not mean it's the best one, so try to be careful when you assume uniformity. It should be a distribution for continuous events on a continuous sample space, where the rate or proportion is constant. Events must be approximately independent of each other, and most importantly, in my experience, the event must be clearly bounded between two values, a minimum and a maximum. In practice, a uniform distribution is closely associated to the definition of randomness. When you hear something is truly random or a random choice, you usually mean to say it's uniformly random. The function random real, for example, and most pseudo-random functions assume uniform probability. Okay, time to apply. In any uniform distribution, what's the probability that a random point is at the left of the mean? Intuitively, half of this symmetric distribution is at the left of the mean. But let's confirm that intuition. Consider the probability x is less than the mean of a uniform distribution, where x is the same as the distribution. And by simplifying the expression, you get indeed 1/2. The angle of a radio signal is often uniformly distributed. So imagine that angle being between 0 and 2 pi, and your reception device only detects an angle from 1/4 pi to 1/2 pi. Then calculate the probability of the angle being at that range, and you get 1/8. Still dealing with an angle, this time let's calculate the angle of a water fountain between 1/6 and 1/3 of pi. What's the expected distance traveled from the nozzle to the ground? From Newtonian physics, you can use that formula to get the answer. Just get the expectation of the speed v squared times 2 sin of the angle times the cos of the angle divided by the gravitational pull, and you get this formula. The examples so far were somewhat unlikely to be used practically. So let's do a real practical example. Let's say you need to assess the metal production quality, specifically of metal shafts and their housing. The metal shafts are between 48.5 millimeters and 50.5 millimeters uniformly, and the metal housings are between 49 millimeters and 51 millimeters. This can be visualized like this, where the blue is the metal shaft and the orange is the housing. So you need no overlap, but you also want to be at a space of a maximum of zero point 0.5. Then what's the probability a random shaft will fit into a random housing? Well, just take the probability that the diameter of the housing minus zero point 0.5 is less than the size of the metal shaft, considering the distribution of the housing and the shaft. And as you can see, it's relatively unlikely. What if you want to generate samples from a uniform distribution? You can use the random real function or equivalently the random variate on the uniform distribution. There's many ways to visualize a uniform distribution. Just generate a sample and have fun. Uniform randomness is everywhere around us, may it be in the grains of sand, equally sparse on the ground, or the ambient noise around us, as white noise is the uniform distribution in sound. Let's say you suspect the time of airplane glass to break to be uniformly distributed. Then, as usual, load the data, estimate the distribution, and confirm the relationship through visualization. Here, you can see the sample follows approximately the curve. Considering the limited amount of data, this indeed seems to be approximately uniform. So, to summarize, remember that the uniform distribution is a constant rate bounded by a minimum and a maximum. You can use uniform distribution, probability, expectation, random variate, and estimated distribution functions to solve uniformly distributed problems. In practice, you see this distribution frequently associated to noise and randomness in general. But as seen in the beginning, this distribution is very limited and does not vary on X, unlike the next distribution.